Hello everyone, welcome back to this channel. In the previous video, we started with the introduction of differentiable functions. In this video, we are going to continue with differentiability and discuss certain miscellaneous problems based on testing differentiability of the given functions. So let's look at the first question based on differentiability. In the previous video, we saw that differentiability means that the derivative exists, right? And it's a pointwise phenomena. When you say differentiable, you mean differentiable at a point. And if you say differentiable on a set, you mean differentiable at every point of the set. So differentiability, similar to continuity, is a pointwise phenomena. You always test differentiability or continuity at a specific point. In the previous video, we saw that differentiability implies continuity, but a continuous function may or may not be differentiable. So in this video, we are going to discuss some more problems on testing differentiability and continuity. So let's look at the first question, which is a branched function given to us, and we have been asked to show that this given function is continuous but not differentiable at x equal to 1. So let's quickly test continuity at x equal to 1. In 2-3 videos shared earlier on this channel, we have discussed how to test continuity at a point. So moving that way, let's quickly find out the left hand limit of the function at x equal to 1. If you see, the fx function is defined in branches. On the left of 1, this is the answer to fx, and on the right of 1, this is the answer to fx. So when we are finding out limit of the function fx from the left side of 1, then we are going to take this as the value of fx, and hence the answer to the left hand limit of the function is going to be 3. Similarly, when we test the continuity of this function at 1 from the right of 1, again it boils down to 3, and f of 1, you can see that 1 is included in the upper branch of this function, and hence the value of the function at x equal to 1 is also going from this upper branch, which happens to be 1 square plus 2. So we see that the left hand limit and the right hand limit of the function is the same as value of the function, and hence this is nothing but continuity of f at x equal to 1, which means that there's not going to be any kind of break in the graph of the function at x equal to 1 when you try to sketch it. Now let's quickly test the differentiability of this function at x equal to 1. We know that differentiability is tested when we find out the left hand derivative and right hand derivative of the function at the specified point, and the left hand derivative at 1 is given by limit extending to 1 minus of fx minus f1 upon x minus 1, because when we test at a, it's given by fx minus fa upon x minus a. The point under consideration is 1 here, so we find out the left hand derivative by evaluating this limit. Now again, since you are on the left of 1, the value of fx is going to come from the first branch of the function, because this is covering x less than 1. So substituting that value here, fx is x square plus 2, f of 1 falls in the first branch again. So f of 1 we can see is 3 here. So f of x minus f of 1 upon x minus 1, when we simplify it, boils down to limit extending to 1 of x square minus 1 upon x minus 1, which is a 0 by 0 form. You can either apply the rule, or if you observe that it's a formula a square minus b square at the numerator, you can just cancel out x minus 1 to evaluate the left hand derivative at x equal to 1. It comes out to be 2. Now on the similar lines, we can calculate the right hand derivative at x equal to 1 by just considering the right side of 1 for the value of fx. So it's obviously going to come from the lower branch, because this covers the right side of 1. So that modifies your limit into limit extending to 1 of fx becomes x plus 2 minus f of 1 upon x minus 1, which boils down to 1. We can see that the left hand derivative answer is 2 and the right hand derivative answer is 1. So left hand derivative is not the same as right hand derivative, and hence the derivative does not exist at x equal to 1, or we can say that f is not differentiable at x equal to 1. We know that differentiability is connected to the smoothness. And if there are sharp points in the curve, then you will not have differentiability. And we saw that differentiability implies continuity, but a continuous function may or may not be differentiable. And this question which we are discussing as the first question of this video, happens to be one such function. It is a continuous function which is not differentiable at x equal to 1. A quick look at the graph of this function is going to make things more clear to you. You can see that the function is a parabolic function up to x equal to 1 because it's following the parabola y equal to x square plus 2 on the left of 1, and on the right of 1 there's a sudden shift, there's a sharpness in the curve at x equal to 1 and it goes along the straight line. So this point 1, which happens to be lying on both the curves y equal to x square plus 2 and y equal to x plus 2, you can see that there is no break in the curve at x equal to 1, but yes, it's not smooth, and hence you have continuity but no differentiability at the point which is the break point of this function x equal to 1. So that's how you can visualize differentiability and continuity through graphs also. Let's move on to the second question quickly. Now look at the second question. There's a function which is defined to be x times sine of 1 by x for x not equal to 0. Since you're talking about sine of 1 by x is not going to be meaningful in R if you take x equal to 0, and hence 0 has been separately defined here. The function has been defined separately as 0 at x equal to 0, and once again the problem says that you have to prove that it's continuous but not differentiable at 0. So beginning the same way, let's first calculate the left hand limit and the right hand limit of the function at x equal to 0. Now you can see that left and right of 0 are going to get covered from the same branch, which is the upper branch, and f of 0 is going to come from this branch of the definition of the function. So f of 0 is given to be 0 for other values which are different from 0. Your value is x into sine 1 by x. So you actually don't need to do left and right. Left and right are going to be limit extending to 0 of x into sine 1 by x. Now when x tends to 0, this tends to 0, and this function is something, sine is a function which is bounded between minus 1 and 1. This we know. So this is something which is a finite real number. A finite number times 0 is always 0. We know that 0 into infinity is an indeterminate form. So if you have 0 multiplied by anything, you cannot straight away write a 0. You have to ensure that 0 is multiplied with a finite number for your answer to be 0. So that happens here luckily, because sine is a bounded function. Sine never goes beyond 1. So it's not an infinite value. So sine 1 by x being a bounded function times 0, the answer to this limit happens to be 0, and this is what I've written as a hint for you to remember forever, that 0 times anything is 0 provided that anything is a finite thing. Okay, you cannot say 0 into infinity is 0. It is an indeterminate form. 0 into infinity is an indeterminate form. You'll have to either make it 0 by 0 or infinity by infinity to actually determine the final value. But if you are sure that 0 is getting multiplied with something finite, then the answer is certainly 0, and hence the limit is existing and coinciding with the value of the function which is given to be 0 separately, and hence you have continuity of the function. But when you try to test your differentiability at 0, once again you consider limit extending to 0. Your point A is 0 here. So the limit that needs to be tested for differentiability is fx minus f0 upon x minus 0. Fx is given to be this, f0 is 0 upon x minus 0. You see that x cancels out because this takes the shape limit extending to 0 of sine 1 by x, because x is cancelling above and below, and we know that sine is a very peculiar function. When x is approaching 0, that means 1 by x is approaching infinity, and when you are approaching infinity, sine we know is an oscillatory function. It's a periodic function. It oscillates between minus 1 and 1. So when x tends to 0, sine 1 by x does not have a limit because it keeps oscillating between minus 1 and 1, and hence this derivative is not existing. The limit fx minus f0 upon x minus 0 is not existing as x tends to 0, and hence this tells us that the function is not differentiable at 0. So it's a continuous curve with some sharpness at 0. So let's look at the graph of this function also to have a better understanding. You can see this is the graph of x sine 1 by x, and you can see what is happening at 0 here. 0, there's no break in the graph. You can see there's no break. It's oscillating infinitely here. So 0 is a point where there is no break, and hence continuity is there, but then you do not have a well-defined tangent here. There is no differentiability at the point 0. You can see that the derivative is not existing through the graph also, but indeed there is no break in the graph, and hence you do have continuity, but you do not have smoothness at x equal to 0, and that tells us graphically also that the function is continuous but not differentiable at 0. Moving on to the next question, you can see this is a peculiar question which is a very famous category of functions which are continuous but not differentiable. In the previous video, we saw that fx equal to mod x was given as an example to justify that continuous function may not be differentiable. We saw that this function is actually mod x minus 0 is continuous but not differentiable at 0. And similarly, you can prove very easily that if you change the point 0 to c, then we can easily see that this function is continuous but not differentiable at c. Now this is an amalgamation, this is a sum of two such functions. Now this function is differentiable everywhere except at 2. This function is also differentiable everywhere except at 2, and hence the sum is differentiable everywhere except at 2 and 3. If we apply that algebra of differentiability, we get the conclusion directly. But let's verify that ab initio also through the definition. If we expand the definition of fx by breaking the real line into segments, into 3 segments, one on the left of 2, one between 2 and 3, and the other one on the right of 3. You can see that when you are on the left of 2, you are on the left of 3 also. So mod x minus 2 will be minus of x minus 2, and mod of x minus 3 will be minus of x minus 3. So when you take their sum, it becomes 5 minus 2x. So the function can be rewritten, this mod, the sum of these two modulus functions can be rewritten as a branched function by breaking up the real line at the points which are specified inside the mod. So that will help you to do analysis in a better way, because we are used to dealing with branched functions in a better way. We can create branches looking at the points, then on the left of 2 you write the answer, take the sum, because this is going to become 2 minus x and this is going to become 3 minus x on the left of 2. So the total answer is going to be 5 minus 2x when you are on the left of 2. When you come to the next segment, which is between 2 and 3, more than 2, less than 3, then more than 2, this becomes x minus 2 only, but this becomes 3 minus x, and when you add them, it's going to be just a simple constant function 1. Again, when you move to the right of 3, when you are on the right of 3, you are on the right of 2 also. If you're bigger than 3, you are bigger than 2 also. So that makes this function as x minus 2 plus x minus 3, which is 2x minus 5. So now you have your function defined in the branched format. So it is very easy for you to see that you just have to test differentiability at the breakpoints. At other points, you do have an answer, a well-defined answer to the derivative. So let's quickly see differentiability at x equal to 2. When you do left-hand derivative at 2, its limit extending to 2 minus of fx minus f2 upon x minus 2, and the left-hand derivative fx is going to come from here. So it's 5 minus 2x minus f of 2 comes from the second branch because 2 is covered here. You can see it's less than or equal to. So f of 2 is also 1. So it's fx minus f2 upon x minus 2, which on simplification gives you minus 2. When you consider the right hand derivative of the function at 2 in a similar fashion, on the right of 2, the value of the function is also 1 and the right side is also 1, because you are in this branch when you are on the right of 2. You are more than 2, so fx value is also 1 and f of 2 is also 1. So that before taking the limit, your answer boils down to 0, and hence the two derivatives from the left and right of 2 are not matching, indicating that the function is not differentiable at x equal to 2. Similarly, we can test differentiability at 3 by considering the left hand derivative and the right hand derivative at 3. For the left hand derivative at 3, the value of the function is going to come from, because this is covering the branch x less than 3. So this is the fx value when you are on the left of 3. So you can see it's 1, and f of 3 is going to come from the last branch. So when you put x equal to 3, it becomes 6 minus 5. So f of 3 is also 1. So that makes the left hand derivative of fx at x equal to 3 as 1 minus 1 upon x minus 3, limit as x tends to 3. Before taking the limit, it's coming out to be 0. So the left hand derivative at x equal to 3 is 0. Similarly, calculating right hand derivative, the answer turns out to be 2, and hence the two answers are not matching. So you have non-differentiability at x equal to 3 also. Thus the given function is non-differentiable at 2 and 3. At every other real number, they are going to be, this sum is going to be differentiable. In fact, if you have any function fx which is looking like x minus, let's say a1, then this is going to be non-differentiable at a1. At every other point it's going to be differentiable. If you compose it, suppose you add x minus a2 to it, then this new function is going to be differentiable everywhere except at the points a1 and a2. Similarly, if you keep on adding modulus functions, then these points are going to be the points of non-differentiability. Every other point is going to give you differentiability or smoothness of the curve at x equal to whatever is the number different from a1, a2, a3. So let's look at this also. Let's look at the sketch of mod x minus 2 added to mod x minus 3, and let's see whether we do have sharpness of these functions at x equal to 2 and 3. You can see this is the point x equal to 2. There's a sharp point here. It was coming along a straight line and suddenly it took a turn in a different direction. So you can see that you do have continuity. There's no break in the sketch, but there is a sharp point. There's no smoothness of the curve at x equal to 2. Similarly, at x equal to 3, there is no break in the curve. So you do have continuity at x equal to 3, but there is no differentiability at x equal to 3. At every other point, you are able to see that it's along one single straight line, and hence you do have differentiability. At the points which are sharp points of this curve, which happen to be x equal to 2 and x equal to 3 here, you do have continuity, but you do not have smoothness. There's sharp point occurring at x equal to 2 and there's a sharp point occurring at x equal to 2, indicating graphically also that this function is going to be non-differentiable at x equal to 2 and 3. So that was about problems based on testing continuity and differentiability. I have listed 3 more problems here for you to practice. You can see that if you modify one of the questions that we have discussed right now, we discussed x sine 1 by x and we saw that it's non-differentiable. But if you take x square or any other higher power, in fact x to power n where n is greater than or equal to 2, you attach sine 1 by x to any higher power greater than or equal to 2, you will start getting differentiability also. So please try hands on this exercise, and if you do have any problem, please post your problem in the comment section. We'll surely we'll surely love to answer your query, but you will easily get differentiability if you just move ab initio, apply the definition of left hand derivative and right hand derivative. You will find that the derivative turns out to be 0. Similarly, a question which is similar to the first sample problem discussed today, you can easily verify that it's continuous but not differentiable at x equal to 1. And then you have a modulus problem. I told you just now that this point is going to be the point of non-differentiability for all mod functions, and hence the answer to this question will be that this function is differentiable everywhere on R except at x equal to 5. At other points it's going to be differentiable. And continuity, of course, it's going to be continuous throughout R. So that is about this video which is about miscellaneous problems on differentiability. I hope you have understood the idea. In the next video, we are going to start with successive differentiation. If you like this video, please subscribe the channel and share this video ahead. Thank you so much for watching.